Good afternoon, everyone, and welcome to day 2 of the eWater software conference. Once again, I would like to acknowledge that I'm hosting this virtual conference on the lands of the Ngunnawal people. I'd also would like to acknowledge the traditional custodians on the land on which you meet today, and to pay my respects to any Aboriginal or Torres Strait Islander people participating in the conference. I pay my respects to elders past, present and emerging, and celebrate the diversity of Aboriginal peoples and their ongoing cultures and connections to the lands and waters of Australia. For those of you that weren't here yesterday, my name is Trudy Green. I'm the Communications and Partnerships Manager at eWater, and I will facilitate today's conference. You should all be familiar now with the Remo platform, but I will just briefly give you a quick run through of some things to expect. If you're having problems, there's quite a bit of information on the Need Support link that you can see on the left-hand side of the screen. We also have our IT support online as well, and Aaron might be able to help you. Please note that if you can't connect, you should still be able to watch even without a microphone and camera. If you're having sound issues, we find that headphones help. The great thing about the Remo platform is its networking features. To take advantage of that, then you should try and turn your camera and microphone on, and you'll be able to talk to the other people at your table, just like in a real conference. You can also move tables by double-clicking on an empty seat, and you'll see on the left-hand panel that there are a number of floors. If you change floors by clicking on one of those numbers, you might be able to find some other people to talk to. And you can also send chat messages either directly to a person or to your table or even to the group. And you can definitely chat if your camera and phone aren't working. Just a reminder that there is an agenda up there in the top right-hand corner, just the little notebook tab. Whilst people are presenting, if you maximise their shared screen, you'll get a nice big image of that, and you'll be able to see all those detailed model pictures. During the presentation, feel free to ask questions by posting a question in the Q&A tab that comes up, and then I will facilitate the discussion at the end of the presentation around your questions. You can vote for questions, so if there's someone else, something that you'd really like to know, then hit on that and it will move higher up the chain. If we run out of time, then I will go to the questions that have the most votes. And finally, if you want to pop a picture in your profile or your name and organisation, that makes it easier for people to find you and chat with you. I'd also like to remind you that today we're running a parallel session from 2 to 4 o'clock, and that's a session dedicated to activities in the Mekong region. We've got some speakers from a variety of places, including the World Bank, the Mekong River Commission Secretariat, and the Cambodian National Mekong Committee. They're going to present on some work that they've been doing using the Source platform and some broader decision support tools. If you want to jump across to that at 2 o'clock, then all you need to do is click on the little icon in the top right-hand corner with the picture of the Mekong River and follow the links. Should you get there and then feel like there's something in the main session that you really want to see, then you will see that there is an eWater logo in the top left-hand corner of the Mekong session, and all you do is follow those links to come back. All right, that's enough from me. I would now like to introduce our first speakers for the day. We have Patricia Lee and Jacob Meehan from Western Water. They're going to present to us about developing a mass balance model to assist sewage and recycled water management planning. So let me just find Jacob and Patricia in the crowd, and I will invite them to the stage. Hi, Jacob. Welcome.
G'day. G'day, Trudy. G'day, everyone.
Alrighty. Well, I will disappear now and leave you guys to it.
Beautiful. All right. So I'm Jacob Meehan. This is Pat Lee, and I guess we'll start by paying our respects to the traditional owners on the land of which we're presenting from. We're both in the west of Melbourne. So traditional owners here are the Wurundjeri and Bunurong people of the Kulin Nation. So we pay our respects to their elders past, present, and emerging. Our presentation is called Developing Mass Balance Model to Assist Sewage and Recycled Water Management Planning. And I guess the aims from the work we've undertaken here were that our modelling shows that there are gaps between the spending we had allocated for capital to go in the ground was leaving, weren't reaching the EPA compliant markers that we needed to have forecast. So we wanted to build a robust model that shows the risks associated with resource constrained planning. If we didn't get all of the infrastructure in, what were the gaps and the risks that we were taking, and this was a tool that we thought helped us do that. Afterwards, we'd be able to paint a path towards getting EPA compliance, which will shape future technical investigations, stakeholder engagement, and realise our strategic opportunities. So Western Water, who we work for, is a water corporation to the northwest of Melbourne. It includes over 70,000 properties, over 3,000 square kilometres, so a bit of an area. It includes metropolitan urban growth areas like Sunbury and Melton with higher density housing. It also goes out to more rural areas like Bacchus Marsh, Romsey, Riddles Creek, where it's a bit more sparse, and then up into the sort of mountain areas of the Macedon Ranges at the bottom of the Great Dividing Range. All those areas are a little bit different climatically. So drier in the south, a bit flatter, and then windier, wetter, more hilly up to the north to Woodend there. I think they got snow. Maybe they got snow this year, maybe last year. We've also got multiple catchments that we're sitting in. So a brief overview of our region here. Our main focus is on our recycled water plants for this project. So we've got 7 quite big ones in Melton and Sunbury, but also smaller ones, lagoon-based plants at Woodend, Romsey, Riddles Creek and Bacchus Marsh. So what we've done in the past is isolated these plants to look at the mass balance and figure out what actions we needed to take. We figured that if we're going to take a 50-year view, maybe we wanted to start looking at the interrelationships between different plants, and we see that we've got a big project at the minute called the Western Irrigation Network, which is connecting up Sunbury, Melton, Bacchus Marsh to an irrigation district just to the bottom left of that picture there. So we sort of thought, well, we've connected those 3 plants and we're sort of shifting the mass balance between them. How can we rejig our tool a little bit so we can look at all the other ones as well? So the end result of the water is we're trying to get it out of our plant into beneficial reuse. We've got a little bit of discharge allowed from Melton, Sunbury, Gisborne, Riddles Creek and Woodend. Each of them can release a portion of their recycled water to the environment, but our main focus is getting beneficial reuse, and we do that through land irrigation, either on our own land that we own and lease out to farmers and operate sort of in conjunction with them, or through negotiating or setting up irrigation schemes. And that's why I put these little purple lines in here, so you can sort of see the extent of where we're reaching our agricultural customers. We've also got residential Class A customers coming off the Melton scheme. So we've got third pipe going to them when we're looking at our ability to source alternate water for people in those areas. But we did find when we set up that Western Irrigation Network, the best bang for our buck is getting those big irrigation networks with a high ability to take water. So I'll hand over to Pat now. If this technology all works, Pat, you there?
Thank you, Jacob. So this diagram shows a typical water cycle in urban areas. Potable water used by customers will become wastewater. Together with rainfall deduced with inflow infiltration, wastewater is conveyed to recycled water plants for treatment. There are losses through the treatment process, and the recycled water produced is stored in a winter storage. Winter storages are typically open basins, which means there is extra volume when it rains, and there are losses through evaporation and seepage. The recycled water is then reused for irrigation. discharge to waterways, or distribute to customers as alternative water after further treatment. We represent our sewage inflow in the model using an inflow node. Jacob, can you go to the next slide? Yep, thank you. So a function has been derived to estimate the sewage inflow based on number of connections, calibrated hydraulic model parameters, sewer master plans, and flow data at the treatment plant. The bottom left figure shows an example of validation results by comparing the model estimation with flow data at the treatment plant for the last 5 years. It is almost impossible to achieve matches on every single day, but a reasonable good match is achieved comparing the yearly and monthly volume. For the future forecast of sewage inflow, we also apply a factor called demand efficiency in the function to represent a sewage reduction per household due to water savings. Therefore, the increase of the sewage flow is different from the increase of connections as shown in the bottom right figure. Next. This slide shows a simple model schematic of a sewage recycled water system. So as mentioned earlier, the sewage inflow is represented by an inflow node. The capacity of the treatment plant is represented by the maximum flow constraint node, which shows the yellow diamond symbol. If the inflow is higher than the treatment plant capacity, the volume will be temporarily stored in a wet weather detention tank as represented by a storage node. The treatment loss is represented by a loss node, which has like a little red arrow symbol there. Treatment lagoons and winter storage are represented by storage nodes. Water taken from the water storage, water is taken from the winter storage according to the customer demand. So any water that is not used is stored in the winter storage. When the winter storage is full, water will spill out to a red gauge node, which represents spills or recycled water to be managed.
So once we got a hold of the figure of the recycled water to be managed at each site, we put together a stakeholder group at Western Water to try and capture all the ideas that have been bouncing around and put it together a big long list of options. This is a pretty simplified view of the discussions and arguments and back and forth that we had, but we've got our little meat grinder here on the left, which represents the modelling process that we've been doing. Included in that is things like expanding residential customers like class A or third pipe sort of stuff, agricultural customers, expanding to potential areas of higher demand. Some of that could mean transferring from the wetter areas to the drier areas where the demand is higher. Also looking at Western Water land irrigation expansion, so maybe purchasing land and setting up schemes like that. And then higher up in the meat grinder, they're not quite ready to go in right now because of some policy barriers and a bit more work that we have to do, but indirect potable reuse, so getting water back into our catchment that can be supplied back to customers as a replacement for potable, and also recycled water for environmental benefit. Things that bounced around a lot and we discussed were economic drivers like floating prices to get more people on board or subsidised water, and also the inflow and infiltration work. So obviously if we get less sewage inflow into our treatment plants, we've got less work to do on the other side. We put them on the bench for now. There's other work being done elsewhere in the business, and the results from analysing the sort of ones in the hopper here can be compared to the work that's been happening parallel, and hopefully we'll get a good answer and get a good understanding of the dip.
So as we are undertaking a long-term planning exercise for the next 50 years, so any implementation of large infrastructure has to be delivered in different stages. So after some internal discussions, we assume the implementation of large infrastructure is staged in 10-year intervals, as illustrated in the top diagram here. When we run the model, we selected a 10-year climate cycle, which is the wettest of the last 20 years, and then we loop the 10-year cycle for the next 50 years. We also simulate the model by coinciding the wettest year near the end of each 10-year interval, as illustrated in the figure on the right. In this example, the blue line represents the storage size requirement in 10-year steps, and the gray line shows the estimated water level in the storage. This model schematic shows how we represent options that involve new irrigation land and storages. So instead of adding 5 new storages for the next 50 years in the model, we represent the storage increments by using a time-varying storage dimension, as shown in the red circle here. Similarly, we model the land irrigation increments using a piecewise linear variable, as shown in the blue circle. There are also times that we may have to release water from the winter storage to the waterways during an extreme wet weather period. We represent this using a function to specify when, how much, and at what rate we can conduct the release. So up until this point, the model schematics that we have shown you is no more than 15 nodes. To give you a bit of context, our mass balance model linking all tanks within our regions is actually look like this. The next slide. Yeah. So the development of our mass balance model does not stop here. There are a number of future potentials and improvements that we could think of that will enhance the capability and robustness of the model. So the first one is testing the model with different climate change scenarios. The current climate model projections indicate that there will be a decline in stream flow in the future with global warming. This means that opportunity for recycled water discharge to waterway may become less viable. On the other hand, demand of recycled water for agricultural use and environmental flow may increase. Simulating the model with climate change scenarios allows us to understand the risk and impacts to our system under the probable climate conditions. This will also allow us to plan and implement infrastructure that are flexible and adaptable to future uncertainties. The second one is constituent modeling. The ability to carry out mass balance on water quality parameters allows us to better understand the impact to the waterway by discharging recycled water. Actions can then be taken to improve the treatment process to prevent adding harm to our environment. It can also assist us to understand the impact to the soil health with land irrigation using recycled water. The last one is urban developer. Currently, we developed our water demand and storage forecasting using spreadsheets and applied in the source model as a function. Using urban developer to undertake the water demand and storage forecasting has the benefit of keeping everything in one place. It also enhances the robustness to test and plan for alternative water supplies in our system. So this is the end of our presentation. Thank you very much for the opportunity to share our experience, and we're happy to take any questions and comments. Thank you.
Thank you, Pat and Jacob. So apologies to those of you out there having connection issues. Hopefully we can resolve them soon. And we don't have any questions through yet, so maybe start thinking about those as well. Whilst they come in, did you find that using this approach, adapting a model that people might traditionally view as a river system model, that you had to be particularly creative, or a water supply is a water supply?
I guess because we know that the source model is traditionally designed for river system, but because we see that the same approach can be applied to recycled water, because like we see the recycled water is not a waste, we see it as a alternative resources. So in a way, it is also a resource modeling or resource planning job. So why not using the same platform? Plus, our model actually is quite interactive. So we start our journey building up a water resource model to start with, but because water get use is not just finished there, and it has to go back to it is a water cycle. So it makes sense to link everything together.
Sure. Okay. One question that's just popped through. This is from Martin Lopesberger in the Northern Territory. He said, it's not a modelling question, but what's the driver for winter storage? No winter demand or making sufficient available for summer use?
Yeah, I guess it's both of those things. It's colder and wetter down here. We run out of daylight in Victoria. We only get like 10 to 12 in the depths of winter, so the crops just aren't helping us out at that point in time, and we need to put it somewhere to save it up for the summer, where the irrigation guys go gangbusters, I guess.
Excellent. Is your recycled water and your potable water models connected? They talk to each other?
Yes, they are. Yeah.
Cool. Excellent. All right then. Well, thank you very much.
That big map
Feel
that we
free
put
to-
up with all the complicated bits on it.
Sure. Excellent. Well, thank you guys. Give you a virtual clap, and
Thanks for having us.
feel free to grab Jacob or Pat at a table and ask them some questions. All right, let me remove you from the stage.
Good.
Excellent. Thank you. Well, I will now invite Marlene Van Der Stern from Water New South Wales to the stage. Marlene has sent me a message that she's about to get a thunderstorm, so fingers crossed this works for her.
It does work. So far, so good. But yeah, the thunderstorm has come and gone already.
Excellent.
Yeah, it's kind of interesting. I'm hearing it thundering in the background and going, "Oh, is it going to make it in time?"
And I will also invite your colleague Rizzana to the stage. So hopefully Rizzana is on her way. There we go.
Yeah, it's getting darker here as well, so maybe.
Well,
So Western Sydney is especially very wet at the moment.
Absolutely. That's a good thing. And these guys are from Water New South Wales, and they're going to present some of their water quality modelling work for you.
Thank you.
Bye.
I'll turn my camera off for now. So go off, Marlene.
Good afternoon, everyone, and welcome to our presentation. We're going to present on the Greater Sydney Water Quality Modelling Project. Rizzana will stay online, and if you have any particular questions, you can either post them in the Q&A or you can just chat with her in the general chat. We were going to share the presentation, but because of the Remo system, we decided just to keep it simple. So talking to you about integrated water quality and quantity modelling for the Greater Sydney Supply System. And internally, we've given it the name Calm Greater Sydney. We developed this project to create a decision-making support system for the whole of the Greater Sydney drinking water catchment, so that we can supply our customers with really good information on what we are providing to them, based on that really good science, the forecast and planning models that we can pull together. This project is actually for our operational team, as well as for our catchment planning team. And it all comes together into the one format. And then we provide information to Sydney Water on what kind of water we'll actually be providing to them, both at their water treatment plant, as well as for their modelling for the Hawkesbury and Nepean model. So our downstream of our systems. So in this presentation today, I'm going to talk you through the concepts and processes that we're going to bolt together and that we are starting to work on. And this project will run for about 3 years. So I'm sure next year we'll be able to provide you an update on where we're at. Now, why are we doing this? We're creating this complex set of linked models for both quantity and quality from a catchment, a reservoir, and a supply delivery aspect. We would like to do this so that we can give those informations to Sydney Water, but as well to better manage the water resources that are coming off our catchments and are managed within our dam, from not just a quantity, but also a quality perspective. It will allow us to do quantitative comparisons and different justifications for interventions and test different solutions that we may have and how this will impact on the water quality in our reservoirs. Further on, once we completed the project, there will be an ability to actually connect in the economic assessments, and we'll set it up in a way that different extensions to the modeling and the operational modeling can be applied to further evolve the modeling. As a result of this modeling project, we're hoping that there will be more robust and efficient operations and will be easier to make decisions based on the modeling outputs coming through. Sort of the model becoming the additional voice in the room that people can listen to. Now, where are we going to do this modeling? The greater Sydney supply catchment. So it's absolutely massive. It's the whole Warragamba catchment, the Upper Nepean catchments, the Shoalhaven catchment, the Blue Mountain catchment, and then a little tiny catchment called Prospect and Reservoir, which is very, very small. So we go as far south as Goulburn and Canberra for the Warragamba catchment, as far east as Wollongong, and as far west as Lithgow and Crookwell, as you can see from the map. So it's a large river system catchment modeling process. Now, what are we modeling? So we're modeling the catchment, the lake, and the supply model. And in those models, we're not only just going to do the quantity, we're also looking at the physical, the nutrients, the pathogens, and the algae. We also are aware that the hydrodynamic model for Sydney Water has 35 plus parameters. And we will have something similar, as a minimum those 35 plus. We have an additional list of heavy metals and metals that are requested to be modeled through this as well. However, not all of that, of course, will be modeled in the catchment model. So that schematic of that outcome, there's some post-processing, there's a whole range that gets done in the lake model. And from the catchment model, there is quite a few that get modeled and quite a few that will be inferred. The way that we're managing the project is around the Agile framework. Not everyone is familiar with that, but what Agile does is really trying to work towards a minimal viable product. So we've adopted the Agile process for modeling, did some tweaks to it. We're running 1 month sprints where the team gets together and does an agreed outcome for the product owner. Once that's done, the month is done, we have a sprint review. We navel gaze in our retrospective, see how we can improve. And then we go back around and create a new plan with the product owners and work our way through their priorities so that once we have something in production, it's their minimal viable product that they can use to make decisions. This is a snapshot of our modeling framework. So we have a range of data on your left-hand side that feeds into the eWater source models and the DHI workbench. The DHI workbench in the middle, in the kind of yellowish, stores all the data, is our workflow process management, and also does our data pre and post-processing. It will call a source model. That source model will be developed based on external advice and other information that comes in. That feeds the results back into the DHI Mark workbench. Workbench then calls HydroHub, in which the 2D modeling takes place using an AA3DM model. That then gets fed back into DHI, and then that gets called upon by an ARC dashboard to visualize it. We'll have 3 different streams of visualization, one for the programs, where it really works around the scenario assessment and program evaluation for the catchment management perspective. There's the decision support output for the real operational selection. Where do I take the water from? What level do I take it from? And how does that mix downstream? And then there from the planning output is the long-term risk assessment. do we account for a different method and different transfers, different programs, and what is the resulting outcome of that? Looking at current catchment conditions, future catchment conditions, current climate and future climate. The key thing, of course, this is a modeling conference, so let's dive into the models. So there will be 3 models: the catchment model, the lake model, and the supply model. The catchment models will be developed for all the declared areas. They'll be done in Source 5. We've started on Warragamba and we're about to go into the Nepean models. And that source model will use the Sydney Water treatment plugin. Sydney Water has been so kind to share the plugin with us and is working with us to make sure that it actually is functioning. And it means that upstream of the dams and downstream of the dams, we're using the same method of modeling the wastewater treatment plants. CSIRO sediment plugin is also going to be used for the sediment modeling, and they've been really helpful in helping us try and pull it all together. The lake model, we use the outputs from the source catchment models as input, and there'll be lake models for all the dams within the Greater Sydney. The supply model takes the lake model outputs, that is also in source, and it will actually use those outflow settings and route them through an upper canal, the pipeline in the river network, to get it through to our supply areas. For the catchment modeling, we've identified the points of interest for our catchment delineation, and each of those points of interest are important for a decision-making point within our business. So we need to make sure that that model output is available for a decision to be made, either for a catchment program or for operations. The modeled parameters within source will be the discharge, TSS, temperature, DL connectivity, the spread of nitrogens and phosphates, and there'll be some E. coli and fecal modeling. That will be followed by the silicates and metals, because we also have some mining discharges. The catchment models calibration and verification process has been assessed. We're using a range of gauge flow data throughout the catchment and using an 80-20 split of the flow. We not only looked at which gauges we can use in regards to making sure there's an 80-20 split of flow, we also ensured that that split has an equal kind of distribution of wet, dry, and average years. Now, as we all know, our catchments are very vulnerable to fire. As we've experienced last year around this time, we're all coughing and sneezing because the catchment was on fire. So we realized that we needed to exclude the fire periods. So we assessed where a fire event had happened and we excluded those time periods from the catchment. Excuse me. We also excluded the following 5 years as vegetation gets reestablished and continues on growing, and reduce that. The excluded periods will be used at a later date to then create a fire land use to be used in the system. This is a snapshot of the wastewater treatment plant developed by Sydney Water. We have a number of wastewater treatment plants within the catchment, and we've parameterized these using the best available data from council. There's some baseline data coming through there that you can see in the graph, and Sydney Water has been very helpful in helping us implement this. Sorry, I'm not the wellest at the moment, so please bear with me. The CSI sediment plugin we've implemented in our trial model. We've been able to get some results out of that. We still need to tweak that and working through some of the gully erosion issues within the catchment and making sure that we have the appropriate data set to underline the modeling. For the reservoir modeling, currently we've got the Elkham-Cadam model that will actually be linking into the system. And as the project develop. So we'll be upgrading the existing lake models to a 3DM model. And the upgrade of this model will be assisted with the help of hydronumerics. Now, this is just an example of what comes out of on one of our reservoir models. But these reservoir models have a large number of parameters. So all of these lake models will be tweaked and modeled and calibrated and validated for a whole range of parameters to make sure that we're able to select the best water quality for our supply system. The post-processing will include creation of these type of images and videos to analyze what happens as a result of an event or where a pollution incident will take place. For the supply system modeling, we decided to go back to source because of the node and link configuration. And the outflow selection from the dams can either take a measured or a modeled output and route them through the network downstream of our dams to allow full mixing of the water supplies. And this also includes full mixing within our weirs, Preston's Nest and Broughton Pass, and that full mixing through the upper canal and the pipeline. So just to focus into our inflows. So we have our different dams where the operators will decide through MikeDHI on what outflows of the dam they're going to put into our supply system. And that then becomes an inflow node into the source system. That then gets routed through. And it gets calibrated at known locations along the canal and the pipeline through the calibration nodes using the parameters flow, level, TSS, temperature, connectivity, nitrogen, and phosphorus, because we have these in line within the system. This then allows us at the water filtration plan to apply a demand and identify the quality provided, but also forecast the quality that will be delivered to our clients in the next week. The whole system is managed through the Mike Operations platform. We have a workflow management process that is used across the operational platform for the rural as well as the Greater Sydney storage operations that follows a similar decision tree process. And the MikeDHI operation platform helps us to take the data in, consume it, prepare it, run the models, and then do the post-processing. And then finally, for the reporting process, we then use that data stored in the database and visualize it in an ArcGIS spatial dashboard, which will allow us to view the results, view the underlying reporting, and underlying decisions that were made from the catchment. The plan is to actually not write a report, but actually have the report available through an interactive process on the spatial site. Now, we've had some challenges. We've had some dashboarding, interfacing, and ICT issues because it's quite an intrinsically complex product that we're trying to create. So as a result, there is high computing demands. There's a lot of interconnective issues that you need to resolve as you go through the development. There's a number of data limitations. There is a lot of data in this catchment. It's one of the well-measured and well-monitored catchments in Australia. But of course, there's never enough data. We also have had GIS data statuses change. Of course, the GDM changed. So we've had to, halfway through the model build, had to update everything to the new standard. The question also came up of how do we model color? So we've got a number of research programs in place, and there's some historical research that is done that we're working through to find some innovative ways on the post-processing of the model results to then infer color. We're looking at heavy metal modeling and working with a research organization to develop some empirical models around that heavy metal generation from our catchment. The question remains around the on-site wastewater modeling. We have a large number of rural areas within the catchment that will have on-site waste management. And we're trying to figure out if that's going to be part of the land use definitions or an overlying parameter that we apply based on a catchment delineation area. Of course, the wastewater treatment modeling, there is always issues with getting data, but the councils have been slowly but surely coming on board and helping us out, which has been absolutely wonderful. The mining impact on the water quality in collaboration with the mining companies is happening slowly but surely, so that we can actually get some information around what their discharges are, and so that we can incorporate those as point sources within the model. Swamp modeling is currently excluded. We have a number of swamps. The question remains, is this actually going to impact the modeling? So the plan is to develop the models and have this as a test case further along, so that we can improve the models once they're built. And of course, everyone had the same challenge, which was the COVID-19 hitting us this year. But because we've allowed Agile and allowed for the Agile project management, we have daily stand-ups, we have daily connection pieces, we see each other on a regular basis online, and we've been able to schedule our work to allow for the changing environments, which has helped us parents as well, where we've had to homeschool, so we just adjusted the workload and the times of work for that relatively quickly as a team. Thank you for listening to my presentation. It's kind of weird not seeing any faces. And I'd like to thank Rizzana for all her hard work this year, and Sydney Water and CSRO for their input and contribution.
Thank you, Marlene. I'll let you grab a big drink of water.
Yeah, I'll have to find some. I haven't got some yet.
That's all right. You might want to stop sharing your screen.
I can do that.
All righty.
Where did Rizzana go?
Yeah, come up and answer some tricky questions.
Yes.
So the first question is probably a $1 million question, I reckon. How do you minimize the model uncertainty and convince decision makers to understand and accept the model result for other planning and decision making purposes?
So the model uncertainty minimization, of course, through calibration and validation in the normal processes. There's not much you can do around that. It's in existence. The communication, however, because we're using Agile, our stakeholders and our product owners and the people using the models have been there from the absolute beginning. So they have been there in the room, understanding the decision we make step by step by step. So as a result, even with the points of interest, so where are we going to delineate the catchment, they endorse that before they even see the model output. So every decision we make is in collaboration with our stakeholders, and we explain very carefully what that decision means for the model outputs. So as a result, you've got buy-in in that uncertainty and the model as you go, rather than here's a model, understand the uncertainty. So that's how we've been working through that to make sure it does meet those planning and decision-making uncertainty boundaries.
Excellent. And you mentioned the problems with the dashboard, but I imagine that's a pretty powerful tool to help decision makers understand.
Yes, absolutely. We're finding that even the little bits that we've already done are being used, even though they're in development still. It's like, can we use it?
Sure. Right, it's a bit of a voting war going on between these next two questions, but we should have time to ask them. Is the economic assessment based on water quality going to be within source or WaterNet?
So the quality will be bolted onto the actual outputs from source, the lake modeling in Elcom or A3DM, the new model, and then source again. So it's going to be a fold-on effect through all of them.
Sure. So
we'll probably take the economic assessment from WaterNet and spit that in as a variable as well.
Okay. And then a second question from Gurmit Singh. Did you look at event-based models with source, the impact of low flows to assess the impact of sewage treatment effluent discharge? It's a big challenge to get the event-based calibration right.
So the long-term planning models will be a 10-year continuous model, so there won't be any events as such in the wastewater treatment plant impacts on the system.
Mm-hmm.
There'll be an event-based model focused on the actual inflows coming in that will use that underlying long-term calibration for the wastewater treatment plants because of that exact issue.
Excellent.
So now the baseline will be a continuous model, and then we'll tweak it for the event modeling.
Very good. Excellent. Well, thank you. And your colleague Ashok says, good presentation.
Thanks, Ashok.
So, oh, actually, I had one more little thing. The dashboard is publicly available, or is it just for decision makers?
Not yet.
Not yet.
But the intent is?
So, and it will be limited publicly. So some things might go to the public website, but Sydney Water will then have access to a bit more, and then we have a lot access to a lot. So it'll be, different audiences, different components of the dashboard.
Yeah, excellent. Thank you very much, ladies. Well done.
Thank you.
Not a problem.
Okay, so that brings us to our first break. We'll take about 15 minutes. Feel free to network at your tables or go grab a cup of tea, and we'll get back at a little bit after 2 o'clock. Thank you.